Imagine collapsing the entire 4.6 billion year history of Earth into a single year. In that compressed view, a month would stretch for over 380 million years. A single day, more than 12 million years. When I try to grasp the sheer scale of time, it almost feels like I'm looking into the night sky, lost in the vastness of it all. It's hard to truly understand the events that have shaped our planet. So let's take a brief look back, shall we? Imagine 140 years compressed into a single second. In a minute, that's already over 8,300 years. An hour, and we find ourselves traveling through 500,000 years of history. If we compress it further, the Earth was formed only 3 years ago. Today, in our compressed timeline, marks the anniversary of the Big Bang, an event that occurred about 2 years before the Earth even existed. It was billions of years after that initial explosion that particles finally combined to form the first atoms. From that moment, the universe as we know it began to take shape, with space, time, matter, and light all coming into being. The formation of gas clouds and the relentless pull of gravity led to the birth of the first galaxies, stars, and planets, including our own solar system. The solar nebula, a swirling cloud of gas and dust, gradually condensed and eventually collapsed in the center. About 19 hours before the birth of our sun, something stirred within that cloud. The very beginnings of life. The Earth and the Sun appeared almost simultaneously, with celestial dust swirling around them. After a few thousand years, or just a few minutes in our compressed time, the dust began to clump together, forming the planets. Telluric gas in the cloud also played its part in this cosmic dance, and so, 4.6 billion years ago, or what we mark as January the 1st on our compressed calendar, the Earth took its place near the Sun. Only 19 hours had passed since that primary nebula disintegrated. During that time, countless dust particles coalesced, forming planets and defining the very shape of our universe, all revolving around the Sun. Gravity then drew them together to create our planet. But the Earth that was born was far from the welcoming world we know today. It was surrounded by a gas shell, a primordial atmosphere like a protective cocoon, but it lacked even the slightest trace of oxygen. The planet itself was a giant molten rock, kilometers in diameter. In those early days, the Earth existed in a state that our minds can only describe as utter chaos. The air was unbreathable, volcanic eruptions constantly shook the surface, and temperatures soared above 2,000 degrees. For a time, there were no significant changes. The Earth remained extremely hot, unbreathable, and hostile to any life that might have dared to emerge in that harsh landscape. However, on January 3rd, a significant event was brewing. Approximately 36 million years after the birth of our planet, something occurred that would forever alter its destiny. Our planet, which seems to rotate invariably around the same axis since its very formation, was not alone in its orbital trajectory around the Sun. There was another celestial object about the size of Mars, also orbiting the Sun along a similar path. This object was called Theia. Up until this point, its presence hadn't posed any problems for either Earth or Theia. But on January 3rd, Theia suddenly veered from its point of gravitational equilibrium and collided with our planet at a staggering speed of 40,000 kilometers per hour. The impact was so powerful that it completely destroyed Theia. Billions of particles that made up Theia, along with billions of tons of rock from the Earth's crust, were hurled into space, scattering into the void. Revolving around the remains of Earth and under the influence of constant gravity, these particles gradually coalesce to form the Moon, our constant companion. In just a few days on our compressed calendar, our natural satellite would complete its final orbit around the Earth. But the Moon wasn't the only consequence of this cataclysmic impact. The Earth also became increasingly massive, approaching the mass of our neighboring planet, Venus. This increase in weight not only amplified gravity but also allowed for the preservation of another atmosphere. That celestial blow also contributed to the formation of a denser core, which now functions effectively as a shield. This magnetic field reliably protects the planet from solar particles and winds emanating from our star. This was one of the most crucial events that had to occur for life to even be possible. But such impacts, although on a smaller scale, were just the beginning. Life on Earth was about to experience a real barrage of meteorites, asteroids, and comets. It would seem as though space itself was collapsing upon our planet from all sides. However, despite this seemingly grim prospect, not everything was lost. Constant volcanic degassing gradually contributed to the formation of the first atmosphere. The Earth, you see, is only one piece of a complex puzzle. Imagine an asteroid just a few kilometers wide, colliding with the Earth. In a fraction of a second, the liquid water that formed the oceans would evaporate. It's hard to fathom the sheer energy of such an event, how it would alter the climate and the very geology of our planet. Our atmosphere, you see, is one of the key players in this story. The gases released during Earth's formation, carbon dioxide, methane, ammonia, nitrogen, and water vapor, they were the raw materials. Gases released during lava eruptions added to the mix. Then, about 4.4 billion years ago, water vapor in the atmosphere condensed and fell as rain. This rain, relentless and unending, filled the smallest cracks in the Earth's crust, carving out lakes and seas in every corner of the world. I can almost see it, those heavy rains, 10 times more intense than any tropical downpour we know today. And they just wouldn't stop. Even asteroid impacts couldn't halt the cycle. Of course, that water didn't just appear once and stay put. For millions of years, the oceans would evaporate, condense, and fall again as precipitation. An endless cycle that continues in its own way, even now. That first geological appearance of Earth was already taking shape. Continents separated by vast oceans. As the Earth cooled, the lithosphere, the solid shell of crust and upper mantle, began to harden. This lithosphere rested on the asthenosphere, a solid layer with the elasticity to allow movement. These tectonic plates, shifting in response to the Earth's internal activity, would separate, collide, and unite, constantly reshaping the oceans and continents. Around February 8th, the first continental land masses began to form, likely small and scattered at first. There was intense volcanic activity, with solidified matter accumulating as the Earth continued to cool and solidify. This marks the beginning of the Archean Eon, when matter accumulated for tens of millions of years before true continents could form. But even before March, proto-continents were starting to emerge. These early land masses were primarily composed of mafic and ultramafic rocks, igneous rocks rich in magnesium and iron, water and igneous rocks, the very foundation of our planet. By the end of March, almost a quarter of Earth's life had passed, and there's no sign yet of even the most primitive life forms. The Earth's crust was still incredibly hot, constantly bombarded by the elements, with oceans evaporating as quickly as they formed. But around March 3rd, something shifted. The ocean basins began to take on a more stable shape as the Earth's crust cooled and hardened. It seems the planet finally reached a point where conditions were right for a habitable environment. I picture a small drop of water falling from a moisture-filled sky, settling into a depression in the rock, forming a tiny pool. We're still far from the sound of waves or the scent of sea dew, but there's something soothing about that water. On January 1st, nothing seemed so peaceful. But as this mass of water accumulated, the volcanic eruptions subsided, and the chaos of the rocks seemed to yield to the water's surface. The Earth was born on January 1st, but life wouldn't appear until March. The first life forms, bacteria feeding on sugars, emerged in the primordial ocean approximately 3.8 billion years ago, about 3 months after the planet's birth. This eventually led to the development of the first form of photosynthesis. Then, on March 24th, something truly remarkable appeared. Stromatolites. I've always been fascinated by the idea of time, how it stretches and compresses, especially when considering the history of our planet. Imagine for a moment the Earth as a cradle, not for a single child, but for all life. It's in the depths of the ocean basin that life first stirred, in the form of the simplest single-celled organisms. It all began there, relatively recently in cosmic terms, with those first forms of microbial life. These cyanobacteria, actively developing in shallow waters, formed a kind of living carpet. They weren't just passive inhabitants, they were microbial traps actively binding sediments. Over vast stretches of time, these processes formed fossilized structures, layer upon layer, structures we can still discover today. For hundreds of millions of years, these cyanobacteria shaped not only their immediate environment, but also the very atmosphere of Earth. From these tiny, simple fragments of single-celled life, dynamic relationships between the heavens and Earth began. The real peculiarity of these organisms was their use of photosynthesis to produce oxygen, an element practically unknown before their arrival. This first form of photosynthesis, known as anoxygenic photosynthesis, differed from what we know today. The bacteria didn't use oxygen. Water molecules served as a source of electrons, but instead of oxygen, they released sulfur as a byproduct. The original atmosphere, devoid of free oxygen, provided ideal conditions for these cyanobacteria. These anaerobic organisms didn't require oxygen and thrived regardless of its presence. In the equivalent of our March and April, the water wasn't too deep, allowing the cyanobacteria to multiply actively. 3 months later, in June, they evolved further, learning to use oxygen in photosynthesis, splitting water molecules and releasing oxygen. These were the first organisms capable of oxygenic photosynthesis. The oxygen-rich atmosphere was taking shape. Just before mid-June, besides these microbial life forms, there were no other species. But even from a bird's-eye view, it was clear that life had firmly established itself. For miles around, one would have seen water and land resembling rocky deserts. Our planet was on the verge of a grand revolution. The emergence of what I think of as Bacteria 2.0 marked a new stage in biological history. The atmosphere was accumulating more and more oxygen, a pivotal moment, providing enough life on the chessboard to truly conquer our space. Before this, the atmosphere was devoid of oxygen, filled with elements like methane, ammonia, water vapor, and carbon dioxide. But the advent of cyanobacteria and their photosynthetic abilities changed everything. Their reproduction led to the production of vast amounts of oxygen, which accumulated in the atmosphere, forming the ozone layer. This gas, composed of 3 oxygen atoms, isn't the main component of the atmosphere, yet it constitutes about 8% of its volume. Within a million air molecules, ozone creates a crucial protective layer in the stratosphere, about 20 kilometers up. This layer absorbs ultraviolet radiation, which is especially dangerous for living organisms, particularly humans. Even amidst this biological revolution, the Earth continued to experience significant geological activity. Plate tectonics, collisions with celestial bodies, and volcanic eruptions. These seemingly chaotic phenomena were integral to the processes affecting the Earth's crust, constantly changing the physical and chemical properties of rocks and minerals. Around mid-March, we see the formation of striped, ferruginous, sedimentary rocks, consisting of alternating layers of iron-rich minerals. The interaction of iron and oxygen in seawater created a unique environment that further facilitated the evolution of life. Over the next several 100 million years, this phenomenon intensified, fundamentally shaping the direction of life's development on our planet. It was at this point, with oxygen levels rising, that aerobic organisms, those requiring oxygen for growth, began to develop. This opened new horizons for the evolution of life forms. By June 14th, life on Earth had dramatically changed. The simplest single-celled organisms were no longer the only players. New, complex, multicellular forms of eukaryotic life emerged. This marked the beginning of the Proterozoic period in the planet's history. In mid-November, our planet experienced climate disruptions. 3 major periods of intensive development followed: glaciation and the birth of one of the first ice sheets. Shortly after celebrating the appearance of atmospheric oxygen and hollow iron in the ocean, the first period of glaciation began. The Earth was completely covered in ice, the oceans frozen into a layer several kilometers thick. From above, it would have seemed like a giant snowball. Gradually, with the onset of the first ice age, the Earth began to shed its mantle. Soon after, one of the first ice sheets appeared. Orogenesis, the formation of mountain systems on unstable parts of the Earth's crust under significant compression, was underway. One of the largest mountain-building events of that time was the Huqui orogeny, which formed what we know today as the Precambrian Canadian Shield and the North American Croton. It's easy to forget, looking at a map today, how much the very ground beneath our feet has shifted and changed over millennia. The cooling and solidification of magma and lava formed the geological core of the North American continent, a process that led to the creation of the Laurentian orogenic belt, the largest of its time during the Paleo-Proterozoic era. It was a time of great geological upheavals. At the end of September, around the 20th, a second aerogenesis occurred, linked to the formation of the supercontinent Rodinia. This, along with the great Pan-African aerogenesis around November 1st, stands as one of the two most important events in Earth's history. If we were to summarize this portion of our planet's story, we would distinguish three periods of glaciation, three aerogeneses, and three supercontinents in the Proterozoic. Columbia formed in August, Rodinia in late September, and Panotia in mid-November. Those few months were a particularly tense period, climatically and geologically. But within that time, many events also unfolded in the world of living beings. As we approach the end of August with only a few months of this Earth year remaining, it's important to carefully analyze this era and appreciate everything that our planet has given us. The first living organisms appeared at the end of March, but it took another 5 months for them to really begin developing. Not long after the first aerogenesis, eukaryotes discovered mitosis between the two meteorite falls. This meant that their stem cells could divide into two genetically identical daughter cells, a small but significant revolution in evolution. But that was only the beginning. Just a few days before September 1st, scientists began to consider the possibility of endosymbiosis and the characteristic evolution of eukaryotic cells. If this theory holds true, then the host cell, by absorbing photosynthetic cyanobacteria, formed the first symbiotic relationship in the history of our planet. This allowed eukaryotes to master a new process of reproduction, meiosis. This new phenomenon took almost 4 weeks. Unlike mitosis, meiosis creates 4 gametes, each genetically unique, a truly monumental leap in the evolution of living organisms. Modern scientists have uncovered numerous microfossils dating back to this period, though they remain largely unclassified. Time has obscured the details, leaving us with limited knowledge. Still, we can be certain that they existed. Eukaryotes were large creatures with shells made of chitin, a flexible and durable organic matter that today forms the cuticle of insects and other organisms. These are believed to include arthropods and limbs of all shapes and sizes. Microorganisms likely constituted a significant portion of the plant life inhabiting the oceans, creating new living beings far removed from the first bacteria we previously observed. The ability to create a variety of cells opened up many more possibilities, and these cells spread widely among living organisms, quickly adapting to different living conditions. Life in that era led to the emergence of fauna around November 13th. We are now witnessing a pivotal moment in the history of life on our planet, the appearance of ediacaran animals. Among them, Namocladus stands out, an animal with a calcified skeleton, classified as a living organism that was able to capitalize on the accumulation of oxygen in both the atmosphere and the oceans. Namocladus is one of the few surviving witnesses of this period, while most of its contemporaries had soft bodies that didn't preserve well in fossil form. However, we can find traces of them in sediments, giving us a glimpse into their presence and the variety of their forms, such as Yorgia, Dickinsonia, and tubular organisms. Tribrachidium, resembling plants, is also found in this region. This oceanic organism, shaped like a feather, lived firmly attached to the bottom, filtering water and feeding on microorganisms known as rotifers. Finally, we observe noticeable changes in the world of algae, particularly in how they adapt to new conditions. Green plants are a group that promotes diversity and aids plants in transitioning from aquatic to terrestrial environments. However, not just green plants, but also red and brown plants contribute to the formation of the first ecosystems. Marina Eleozoica concludes her speech with great news for all life on the planet. Beyond the significant environmental, geological, and climatic changes that occurred during the Proterozoic period, Marina highlights the transition from single-celled life to multicellular organisms. At the geological level, Earth's activity remained intense, evidenced by various aerogeneses and continental evolution. This underscores the dynamic and constantly changing nature of our planet. Events arising from this active activity happen continuously. We are nearing the end of our year, the year representing the entire life of Earth, from its inception to the present day. Its history is drawing to a close, yet much remains to be discovered. Today is November 17th, and only 44 Precambrian days separate us from the emergence of the first multicellular animals and the present day. The days from November 17th to 21st will be particularly special for our planet, marking one of the most significant events in its history, almost 11 months into the Earth's year. These 11 months represent the Precambrian period, during which we observe the evolution of life on Earth after the Archaic and Proterozoic eons. Between November 7th and 21st, we enter the Paleozoic eon. The Cambrian is the first era of the Paleozoic eon, a time when new animal groups spread rapidly, leading scientists to speak of an explosion of life. I sometimes think about the moment when the Earth truly changed, a moment when the very order of things shifted, and the trilobite became a symbol of a new era. These marine creatures, with their shells preserving invaluable evidence of the past, represent a crucial step in the development of life in the oceans. Unlike the simpler animals that came before, trilobites demonstrate how life evolved toward greater complexity. They lived in seafloor biotopes teeming with arthropods, crustaceans, and even early mollusks like gastropods and brachiopods. While these ancient seascapes weren't quite modern, their diversity was astounding. Among this abundant life swam the Anomalocaris, resembling a small centipede gliding along the seabed. There were also unusual creatures like Pikaia, a possible ancestor of the Canadian yeasp, and the peculiar Lucius. Then there was the haloid trilobite, Vivaxia, always wary of the Anomalocaris, a fearsome predator beginning its hunt. Even then, the relationship between predator and prey was fundamental. While many creatures were suspension or filter feeders, Anomalocaris was the first true predator in the history of life. Its evolution was remarkable, possessing compound eyes with 16,000 facets, a mouth, teeth, legs, fins, and a long tail. This was far removed from the single-celled organisms of the Precambrian period. Specific organs were emerging, driving the increasing complexity of ocean life. At first glance, the ocean might seem like a picturesque haven, but on land, conditions were harsh. Rocks and dust severely limited the possibilities for life. The ozone layer, though thickening, was still too thin to adequately protect the continents. Without this shield, ultraviolet rays could destroy any unprotected organism. For miles, there was no vegetation. The continents, devoid of a protective green cover, were in a deplorable state. The Gangwan continent, encompassing what we now know as South America, Africa, India, Australia, and Antarctica, was particularly affected by intense erosion. It was a dry and desolate landscape. During this period, the Earth was experiencing turbulent times. While the Northern Hemisphere remained lifeless, the Southern Hemisphere became home to impressive continents. Besides Gangwan, there were Laurentia, Siberia, and Baltica. These continental masses were not stationary. They were constantly moving and rearranging themselves. These shifts caused the Rake Ocean to open in the south and the Iapetus Ocean to begin closing. This plate movement undeniably influenced life and the activity of the ridge. For instance, in the area of Puerto Rico, the oceans actively penetrated the continental shelves, with the water level rising significantly. Perhaps this is what allowed plants like Marchantia polymorpha to thrive. Life on land was still limited. We were far from creating a rich and diverse biotope on the continent. However, the appearance of this liverwort offered a glimmer of hope for the future. But let's return to the ocean. By the end of this period, marine life had recovered and diversified. The cephalopod Syntybucs, though only 30 meters long, swam these waters. And of course, the orthoptic trilobite, an animal that truly personified the Ordovician period, was present. Among these ancient marine inhabitants lived Megalograptus, also known as Euripus, a sea scorpion reaching about 80 centimeters in length. It preyed on trilobites, which were likely in decline. While some groups of animals continued to develop and expand, others became more diverse. Among them were canodonts, promis, and cephalopods, reaching several meters in length. They actively exploited the resources and shelters provided by sponges. The marine kingdom also housed brachiopods, solitary corals, and ovlacs. Paleobiological data, accumulated by researchers and representing a collection of information on more than 30,000 fossils, remains a valuable resource for studying the Paleozoic world. The geological and climatic characteristics of this period included a decrease in temperature. Perhaps this marine abundance was facilitated by underground waters, which dropped from 45 to 30 degrees. This significant change undoubtedly impacted life. Aquatic phytoplankton and algae attached to the seafloor were among the first to benefit. These early organisms also benefited from expansion, leading to a domino effect. Reproduction at the base of the food chain allowed filter feeders, herbivores, and other primary consumers to develop and diversify. Of course, predators didn't stay away. They began to return to land. Although still fragile, it was an incredible event. The conquest of the continent by living organisms, and at this point it was only a matter of time. I find myself continually drawn back to the image of those first mosses. Imagine life making its way onto the continent, settling on the edge of the water, finding purchase on dry land where only rocks, sediments, and minerals had been before. Marchantia polymorpha, one of the very first plants to establish itself firmly on Earth, alongside mosses and bryophytes. Their spread, almost unbelievably, accelerated the chemical erosion of volcanic rocks on the continents, reducing the concentration of CO2 in the atmosphere. The weathering of those continental rocks also released massive amounts of phosphorus, which rivers then carried into the sea. This enrichment profoundly impacted marine fauna, fueling the development of phytoplankton, boosting photosynthesis, and encouraging the emergence of countless new species. It enriched the biotope and created conditions for the development of new ecological niches. If things were going well for the marine life and for all living things, it would seem everything was ideal. But there was a catastrophe looming. It arrived on November 24th, lasting mere minutes. The Ice Age, which would end with the extinction of some families and half of all animal species. Sailors call it the second largest extinction the Earth has ever experienced. After the Permian period, photosynthesis increased, undoubtedly the reason for the reduction of CO2 levels in the atmosphere. This led to the famous Ice Age period, a serious biological crisis. Rising sea levels were the first sign that life had to overcome this crisis. Biological nature had to adapt to this renewal, and it would not be the last. Then, on November 25th, we enter the Silurian period, and the flora and fauna must adapt to new conditions. Although reblooming might only take a few hours in this accelerated view, in reality it could take thousands of years. But the Earth has plenty of resources. It doesn't give up easily. The warm climate helps coral reefs to thrive, reefs inhabited by tetras. Coral reefs and tabular fish mainly occupy the edges of the Pantalas and Paleotti in shallow water. Melting polar ice leads to rising temperatures. The general rise in sea level and shallow waters now cover continental shelves, platforms that reflect geological events. It's important to pay attention to the mountains, too, as they are evidence of slow but constant movement. But let's return to the ocean and see how life is gradually returning to normal. During the Silurian period, under the rule of Eupetus, there was a significant rise in the development of new groups of organisms. A few days ago, during the Ardan period, jawless fish appeared, but it was during the Silurian period that these fish underwent a real evolutionary leap, and algae and vascular plants began to develop actively. After appearing on the continent, life gradually takes hold thanks to the emergence of a colony of plants. The first green cover appears on the banks of rivers and seas. And the appearance of these plants gave impetus to the formation of a small ecosystem. Although the ecosystem is still in its infancy and very fragile, it grows and develops promisingly, becoming reality with every second. Look closely at the ground. A new inhabitant has already settled in. In this small nook of vegetation, you can see the first Scorpio who dared to take a few steps on dry land. But this is not the only amazing creature. Spiders and ground insects also live here. Centipedes like this pneumatic centipede. One of the most interesting features of its skeleton include the presence of stigmas, or holes. Trochines are among the first living creatures that began to walk on land. Until now, almost no one else on Earth could do this in water. Here, the support is different. You need to maintain your own weight and air press, as well as breathing differently and moving around without the aid of water. The animals you just saw are pioneers in achieving this goal. A feat on Earth is always a sign of significant changes. At first, within a few hours or a maximum of a few days, things happen quickly. In geological terms, this sets in motion radical and new processes. The Dimic period was not only the end of calcific aerogenesis, but also the beginning of the Hercynian. For animals, it began suddenly. Between November 28th and December 1st, eternal osteostrong, which occupied a dominant position in the animal world, suddenly disappeared, freeing space for new species. In just a few hours, new groups emerged, such as Lopidae-breathing fish, impressive localites, gill plates, osteopiforms, and coelacanths. The aquatic world has become more active than it was a few years ago. These days, animals are very different from those we've encountered before. Now we see ones of impressive size, predators adapted for hunting. One of them is Dunkleosteus, which attacks the cladocoloc shark. Other predators, such as the rollpis, which are attacked by schools of acanthoid fish, are also distinguished by their size. Among fish, we are observing an important process: the radiation of ray-finned fishes, or ray-finned fishes, like this Chaerolepis, which are increasingly populating the world's oceans. Another important group, leaving their mark on the seafloor, Sarcopterygia, bony fish with fleshy fins. They appear alongside cartilaginous fishes such as sharks. We just became witnesses to how the ocean's architects continue to create their masterpieces, such as Estimatoplasty. These amazing structures are home to hundreds of different species, including some brachiopods and goniotites, cephalopods. Curled up on the ground, the landscape has never been so peaceful and calming. Even though the plants here are small, I've always been fascinated by landscapes shaped right before my eyes, a process we rarely get to witness so directly. Imagine a world where the first trees in history, arborescent club mosses, dominate the landscape. Most stand about 10 meters high, creating a vast green carpet. If you look closely, you'll notice patches where the plants are taller, greener. That's the weekly club moss, blooming in May, reaching about 50 centimeters in height. But this isn't the only plant life here. Venture a little further and you'll find yourself in a region of opalax where the temperature hovers around 28 degrees with incredibly high humidity. At the water's edge, the smallest plants take hold, club mosses and clerics, giving way to bushy, scaly bushes of radon under Tetraxa. These plants form the border of a young forest where herbaceous club mosses thrive. Most impressive of all, however, are the arborescent club mosses, the first trees. The largest of these, the Eopermat pteris, reaches about 8 meters tall, resembling palm trees. With the emergence of such vegetation, new ecological niches began to open up. Extensive cottontails, like Renella's predecessor, occupied the territory. But the most exciting development was the appearance of the first four-legged creatures. On the morning of December 1st, a creature we call Tikal, the first four-legged being, was born. And not long after, around 8 p.m., another aquatic organism, their Auteriosis, emerged onto our blue planet. It was one of the most ancient tetrapods, retaining features of a fish with a caudal fin, tail, and belly covered in small scales. They also possessed the first true limbs with 3 joints: hip, knee, and ankle. Their theothyroidism became widely known for being among the first aquatic vertebrates to attempt moving onto land, adapted for both swimming and terrestrial movement. However, this good news for life on Earth came with a shadow. The depletion of oxygen in the oceans triggered a new mass extinction, devastating the planet and wiping out nearly 75% of species. Then, on December the 2nd, we entered a new period, the Carboniferous, marked by the collision of plates. The European, American, and organic masses continued to form the Hercynian chain, uniting nearly all continental parts into one supercontinent, Pangaea. Within hours, Pangaea faced intense erosion, accompanying the formation of the chain. Arnica, combined with the lush vegetation of the Carboniferous forests, continued to draw down carbon dioxide from the atmosphere, affecting the planet's temperature. The continental masses of the South Pole began to ice over, foreshadowing a new crisis. Let's return to biology. In December, a significant temperature difference emerged between the poles and the equator, leading to a zoning of vegetation. Dense charcoal forests with lepidodendrons covered the equatorial zones. In temperate climates, deciduous trees like Glossopteris became more widespread. Gradually, more diverse plants populated the swamps, fostering further diversity in life. New ecological niches appeared, and plants that reproduced by seeds spread, occupying more and more territories. The vegetation cover grew more diverse and dense, contributing to the development of terrestrial fauna. At the beginning of the Carboniferous period, on December 3rd, numerous amphibians such as the actinodon appeared in the swamps. These swamps teemed with life. About 100 species of spiders and scorpions, as well as the first flying insects, such as swarms and giant dragonflies. Among them was the Meganeura, a dragonfly with a wingspan of nearly 70 centimeters, and the Artipleura, a centipede reaching 1.5 meters in length. This was a period of gigantism. Scientists believe the immense size of many insects at that time was linked to the high oxygen levels in the atmosphere. During the Carboniferous period, a significant event occurred that, according to scientists, contributed to the increase in oxygen in the air. This increase stemmed from the very process that gave the Carboniferous era its name, the formation of coal. The massive trees we observed became the source of coal deposits. As this carbon was buried in wet soils, the oxygen level in the atmosphere increased by 15–20%, roughly 25% higher than today. Insects, needless to say, thrived in this oxygen-rich environment. Another key event was the emergence of the amniotic egg, a new stimulus for the evolution of new species. Between December 5th and 6th, synopsids appeared and rapidly diversified, creating new groups. Sauropsid species followed suit on December 6th. By this point, the two main groups of synopsids and sauropsids were established. The beautifully preserved emus represents one of the first sauropsids. From sauropsids evolved crocodiles, dinosaurs, and birds. Archaeates, a representative of the synopsids, gave rise to the lineage of mammals. The Permian period marked the end of the Carboniferous, though the formation of coal remained a characteristic feature of this time. A few days into this new period, a fungus emerged with the ability to decompose wood, or at least lignin, putting an end to the formation of coal. Although this fungus marks a significant transition between the two eras, in Peng I find myself constantly drawn to the Permian-Triassic extinction event. Of all the extinctions our planet has experienced, it was undoubtedly the most severe and intense. 96% of species were wiped off the face of the Earth. It's hard to even fathom that level of devastation. Now, as we move forward, we see connections emerging on this dramatically changed planet. Continents like Gondwana and Laurasia are nearing their peak development. The synapsids, which we encountered earlier, are now practically unified. The ecosystems are supported by creatures like the carnivorous lichen from the Gorgonops family. Amphibians, surprisingly, still playing a dominant role despite their earlier prominence. But these amphibians, the first vertebrates to adopt a partially terrestrial lifestyle, are gradually giving way to new species, including synapsids and parasaurs. Consider the Orion pariasaurs, large crouching anapsids adapted to swamp life, much like modern hippos. They possessed strong limbs, walked upright, and were covered in skin armor. These herbivores could reach lengths of up to 3 meters, quite unusual for terrestrial forms at that time. Interestingly, though they started with an animal diet, they gradually transitioned to vegetarianism. It's fascinating to see these early animals choosing to walk upright, perhaps for agility or even to attempt flight, at least in the early stages. Of course, there were many predators around then, including the ferocious pariasaurs. And it wasn't just predators utilizing the Orion arcs. While synapsids were the most common vertebrates, trees remained vital. Some reached impressive sizes, creating ecological niches for insects and small reptiles like cycads. These palm-like plants complemented the forest biotope. But despite all of this life, a biological crisis shook the world. Until then, life on Earth seemed to be proceeding as usual in a natural rhythm of evolutionary processes. Ecosystems, both marine and terrestrial, thrived. But on December 11th, everything changed. Intense volcanic activity disrupted this order. The eruption lasted for what would seem like an eternity, over 500,000 years. Volcanic eruptions formed a 6-kilometer layer of lava. The amount of gas released was staggering, comparable to the total exhalation of every person on Earth. The temperature soared by more than 40 degrees Celsius and oxygen levels plummeted by 7% for terrestrial species and a devastating 90% for marine species. So many marine species disappeared entirely. The life cycle seems to have been interrupted by asteroid impacts and intense volcanic activity. The cause of this unprecedented biological crisis could have been both the Permian and a super era. On that tragic note, the Paleozoic era ended. But as always happens after a crisis, a new stage follows. Diversification, the emergence of new species, and large-scale changes. Evolution, in its fleeting way, returned. Periods followed one another with incredible speed. A shorter, more intense era lasted only a few days, but the changes were enormous from geological, climatic, and biological perspectives. Since the Mesozoic, everything seems to have accelerated. The pace quickens, radiation and biological changes become more intense, species multiply, and life seems to know no bounds. In December, after the deep biological crisis, flora and fauna gradually recovered. Life was returning, but this was only a temporary reprieve. The Triassic period remains unique in history, beginning and ending with a biological crisis. The Earth is vast, and it needs time to recover. Plants overall coped with the crisis quite well. The cycads we saw earlier, along with the drogas and the famous Glossopteris, were still present. The existence of this flora undoubtedly contributed to the return and diversification of the fauna. Gradually, the vegetation of the northern hemisphere acquired a new appearance, becoming more numerous and diverse. Among the animals, we see some losing their status, while others take the places previously held by amphibians. Large areas were occupied by synapsids, which were quite developed, but diapsid reptiles began to find their place in the ecosystem, gradually taking over the continent. The archosaurs, once timid and few in number, now enjoyed the opportunity provided by the biological crisis to occupy the newly available ecological niches. They took advantage of this exceptional radiation, which subsequently led to the emergence of several groups such as crocodiles, dinosaurs, and birds. During the Triassic period, there were crocodile morphs like the Saurosuchus and dinosaurs including L. lager python, L. salizaver, and maracu, who were the main competitors. Just before the end of the Triassic, the first dinosaurs appeared, such as Procompsognathus, which, despite its small size, was a source of terror. The terrible Tyrannosaurus fed on insects and lizards and could also hunt small prey. Scavengers could also be present. You might also encounter a Platysaurus. But don't worry, some amphibians were vegetarians. Who would survive the crisis? Perhaps the Tenospondylus, enjoying the peace and quiet of the swamp. It's an amphibian that lives in the Borgia frog's labyrinth and in the oceans. They traveled the seas in search of food and had a good appetite. Near them appeared other groups, but as long as they remained discreet, they were certainly waiting for their time to reach their full potential. Here we can see one of the first turtles, and probably the first mammal on our planet. This brings us to December 15th. Imagine a world plunged into darkness. That's what it must have been like when the Chicxulub asteroid struck, a cataclysm that would carve out a crater 180 kilometers wide. Dust, gas, acid rain. A suffocating cocktail that extinguished life on a massive scale. Volcanic eruptions added to the devastation, creating a rapid cascade of death. We don't fully understand what triggered this crisis. Perhaps it was the massive eruptions during the breakup of Pangaea, releasing vast amounts of carbon dioxide and altering the climate. Or perhaps asteroid impacts played a significant role, evidenced by craters like the Manicouagan in Canada and the Rochechouart in France. Whatever the cause, the Jurassic period witnessed the disappearance of 70 to 80% of species. But while many perished, the dinosaurs thrived, seizing the opportunity to conquer new territories and adapt to their changing environment. They filled empty ecological niches, leading to increased species diversity. Two major groups emerged, predominantly ornithischian herbivores that roamed in herds and the Saurischian dinosaurs, divided into theropods, bipedal predators, and sauropods, large, quadrupedal herbivores. Among the famous theropods were Allosaurus, Megalosaurus, reaching 7 meters in length, and Archaeopteryx, a crucial link between dinosaurs and birds. The Jurassic period was truly the heyday of giants, like the Diplodocus weighing perhaps 15 tons. But even more impressive was the Brachiosaurus, whose vertebrae alone reached 70 meters in height, with a total length almost double that. But as the Jurassic gave way to the Cretaceous, lasting until December 25th in our geological calendar, the landscape began to transform. The first angiosperms, or flowering plants, appeared. Insects diversified rapidly, with flies emerging in the Jurassic period and bees and butterflies arriving in the Cretaceous. These flowering plants with seeds and nectar changed everything. New species were evolving, some becoming incredibly popular, like the Triceratops, a formidable creature reaching 7 meters in length and weighing 8 tons. But the true heavyweight champion was Argentinosaurus. Dinosaurs began to develop feathers, becoming more common in the Cretaceous period, like microraptors and similar creatures. It's a strange thing to consider. Even 1,000,000 years from now, our Earth will still be recognizable from the sky. Continents will have shifted, yes, but the sun will still rise, the moon will still orbit. However, some things I know will change dramatically. Irreversible geological processes are already at work, constantly transforming the vulnerable coastal ocean zones. Consider the active underwater volcano off the southeastern coast of the Hawaiian Islands, the largest in that chain. It already rises 3,000 meters above the seafloor and grows every year. In 1,000,000 years, it could breach the surface, forming a new island already named Laihi. Meanwhile, the older, extinct volcanic islands to the northwest, Maui, Oahu, Kauai, are slowly being reduced in size by the relentless action of wind and waves. It's these waves, researchers believe, that will play a key role in shaping the Earth's topography over vast stretches of time. The more active the geography becomes, the faster the oceans will advance and retreat, and the rate of rift volcanism will inevitably change. And geography changes slowly, almost imperceptibly in a human lifetime. Sea levels, for instance, can rise or fall significantly, depending on the amount of solidified lava on the ocean floor. When volcanic activity subsides, the rocks on the seabed cool and settle, causing the sea level to drop. Scientists even believe that the sharp drop in sea level just before the Mesozoic extinction event was caused by a lack of large inland seas like our modern Mediterranean. The collision and disintegration of continents also leads to significant changes in the size of coastal areas. So, to really understand how the world will develop in the future, I find myself drawn to the events that took place on this planet hundreds of millions of years ago. The global tectonic processes that continue to influence our planet will undoubtedly play a crucial role in shaping its appearance in the eons to come. Today, the continents are quite far apart. Oceans separate America, Eurasia, Africa, Australia, and Antarctica. But these vast land masses are in constant motion, moving at about 2 to 5 centimeters per year. That's roughly 100 kilometers every 60 million years. By studying the age of rocks, we can determine the vectors of this movement for each continent with remarkable accuracy. Basalt from the ocean floor, for example, provides invaluable information about its age and composition. Basalt near mid-ocean ridges is relatively young, only a few million years old. But basalt found near continental margins in subduction zones can be more than 200 million years old. These age differences allow us to reconstruct the global tectonics of the Earth over the past 200 million years. And with that information, it becomes possible to predict the movement of continental plates for the next 100 million years. Given the current trajectories, it seems likely that the next major continental collision will occur in about 250 million years. The result: most of the land on Earth will once again coalesce into a giant supercontinent. The precise shape of this future supercontinent remains unknown, a subject of ongoing scientific debate, but we can observe the movements and make informed predictions. It's a strange thing to try and imagine, isn't it? The world map for the next 20 million years. It's a puzzle that occupies many researchers, and even if we can't see every detail, some general features are starting to emerge. I find it fascinating to consider these massive shifts, the continents rearranging themselves over such vast timescales. For instance, most agree that the Atlantic Ocean is destined to become the largest, eventually surpassing the Pacific. The Earth's crust, according to the theory of extraversion, will keep expanding, pushing America into a collision course with Asia, Australia, and even Antarctica. It's almost like watching a slow-motion ballet of tectonic plates. North America, in this future scenario, will close the Pacific to the east, crashing into Japan and South America. These land masses will rotate, connecting with Antarctica, forming a supercontinent stretching along the equator. The extraversion model suggests that the mantle cells beneath these plates will largely remain as they are now. Of course, there's another school of thought: introversion. This perspective looks to the past, to cycles of the Atlantic closing and opening, offering a contrasting view. These discussions about supercontinents, extraversion, and introversion are ongoing and quite lively, I as you. Regardless of which theory prevails, there's a consensus that the Earth's geography will keep changing over the next 250 million years, still echoing the past in its patterns according to computer simulations. What's even more remarkable is how these changes will intertwine with the Earth's climate. In about 200 million years, the average temperature is expected to decrease, and the global ocean level could drop by approximately 120 meters. Even with these shifts, conditions for complex life should remain favorable, especially closer to the equator. But fast forward another 200 million years, roughly 400 million years from now, and the average surface temperature could drop by about 10 degrees, with an even more significant sea level decline. Imagine all continents stretching from north to south, covered in glaciers, even in temperate and mountainous equatorial regions. It's a chilling thought, isn't it? Yet this deep freeze isn't necessarily permanent. In the millions of years that follow, a balance should be found between the decreasing temperature due to the loss of bacterial nitrogen from the atmosphere and the increasing solar luminosity. The temporary reunification of continents around the equator might soften the effects of glaciations and reduce sea level changes. Mountain ranges will rise, climates and vegetation will transform, and oxygen and carbon dioxide levels in the atmosphere will fluctuate. It's a constant cycle of change, repeated throughout Earth's history. And then there are the more dramatic possibilities. Sometime between 500 and 600 million years from now, there's a chance, a terrifying chance, that a gamma ray burst, or a supernova, could occur within 6,500 light-years of us. gamma-ray bursts are, as far as we know, the most intense and energetic explosions in the universe. Astronomers believe they're linked to extremely powerful supernovae. Fortunately, we haven't observed any nearby. But if such an event were to happen close to us, it could trigger a mass extinction. A massive burst of gamma radiation, lasting just 10 seconds, could obliterate at least half of the Earth's ozone layer. The consequences for food chains and species survival would be devastating. All life on the Earth's surface and in the upper layers of the ocean could be wiped out. It's a frightening scenario, especially when I consider that a significant amount of our atmosphere's oxygen comes from space. Gamma rays can also destroy oxygen and nitrogen, converting them into nitrogen dioxide, which would create a thick smoke cover, potentially triggering a global ice age by blocking sunlight. Even without such cataclysmic events, the Earth is changing. The tidal forces between the Earth and the Moon are causing the distance between them to increase. Over the past 50 million years, the Moon has moved more than 20,000 kilometers away. In about 600 million years, all eclipses will be annular, and the lunar disk will no longer be able to completely cover the solar disk. Ultimately, the fate of the Earth is intertwined with the fate of the Sun, which, like all stars, cannot shine forever. Since its formation, our star has been a main sequence star, and its luminosity has been increasing almost linearly, by about 1% every 110 million years. I sometimes find myself thinking about the end of the world, not in a sensational way, but as a quiet, inevitable process. It's a strange comfort to consider that even the Earth itself has a lifespan. Long, of course, unimaginably so, but finite nonetheless. In about 1 billion years, our Sun will begin a slow transformation, growing brighter and hotter. The increased luminosity will significantly impact our planet, sending solar radiation to Earth in greater amounts. This change will start to affect the very minerals on the planet's surface. These changes to the minerals will then set off a chain reaction, affecting the carbonate-silicate equilibrium cycle. This geochemical process involving the interaction between carbonates and silicates will be altered by increased weathering of surface rocks. Carbon dioxide will be retained in the soil as carbonate, and as water evaporates from the surface, the Earth's rocks will harden, and plate tectonics will slow. Eventually, when the oceans evaporate completely, tectonics will stop altogether. As volcanic activity decreases, so will the processing of carbon in the atmosphere, and carbon dioxide levels will begin to decline. It's a strange reversal, considering that for the past 600 million years, Earth has experienced periods of extreme cold. But now, the increasing brightness of the Sun is causing the planet's temperature to rise, creating a new set of problems. The first signs of these problems will appear in the next 600 million years. When solar activity increases by just 10% compared to current levels, the average temperature will reach 47 centigrades. In 100 million years, the situation will become critical, and Earth will begin to gradually lose its water. The atmosphere will transform into something resembling a humid greenhouse. As more surface water evaporates, the amount of water in the stratosphere will increase. The Sun's ultraviolet radiation will then break down these water molecules in a process called photodissociation, releasing hydrogen from the atmosphere. The result? The oceans will likely disappear in about 100 million years. For millions of years, water vapor will rise into the stratosphere, undergoing chemical decomposition and separating into oxygen and hydrogen. While these changes occur, the rising temperatures will cause the oceans to absorb more carbon dioxide, which is essential for photosynthesis. But as plant life absorbs it, the level of carbon dioxide in the atmosphere will decrease, disrupting the balance necessary for plant life. According to current projections, the planet can support highly organized life for another 600 million years. After that, the increased solar luminosity will significantly impact the biosphere. It's worrying to imagine Earth gradually losing its precious water and the vital gases needed for plant development. These interconnected elements pose a threat to the fragile balance of our ecosystem, especially in high-temperature conditions. The oceans will absorb more carbon dioxide, which will disrupt the processes necessary for plant life, accelerating the problems associated with water loss and the degradation of our atmosphere. We are nearing the limit of carbon dioxide emissions compensation on Earth, reaching a critical point where the balance between carbon dioxide and oxygen becomes unstable, affecting photosynthesis. In approximately 600 million years, the level of carbon dioxide will fall below what's needed to support C3 carbon fixation, a process used by trees and other plants. While C4 carbon fixers can withstand carbon dioxide concentrations as low as 10 ppm, currently 99% of plants use C3 photosynthesis. As the ability to convert light into energy decreases, there will be a general decline in plant biomass. If CO2 levels in the atmosphere decrease, survival will become difficult for embryophytes, which require a minimum concentration of about 10 ppm of atmospheric CO2. The evolution of living organisms will likely include adaptation to these conditions. Some organisms may use a photosynthetic carbon absorption mechanism that becomes more efficient as carbon dioxide levels fall. However, as complex cells begin to die, oxygen production will decrease. This, combined with continued consumption by biota and oxidation of kerogen, organic carbon, and sedimentary rocks, will lead to a gradual decrease in the level of oxygen in the atmosphere to zero within a few million years. Researchers have calculated that plants using C3 photosynthesis to fix carbon dioxide from the atmosphere should disappear in 600 million years. C4 plants will follow about 840 million years from now, due to the loss of carbon dioxide. This mass extinction of plants will have devastating consequences for all living things. Today, plants are the foundation of the food chain, providing food and energy for herbivores. Their decline will lead to a reduction in food resources for those who depend on them. Unfortunately, plant populations are already beginning to decline, changing the balance of the ecosystem. Without plants producing oxygen through photosynthesis, animal life would be in danger. Animals like mammals and birds are likely to be the first to encounter difficulties, as they are vulnerable due to their high oxygen requirements compared to smaller endothermic and ectothermic animals that will disappear as their numbers decline. Placental mammals will find themselves particularly vulnerable, not only having a greater need for oxygen than non-placental mammals, but also because of their development, especially embryonic development. I sometimes wonder if the last creatures on Earth will even resemble what we now call animals. It's a disquieting thought, isn't it? The idea that beetles able to withstand temperatures up to 56 degrees might outlast nearly everything else. It makes you think about resilience, about what truly matters for survival. Large mammals, I've read, are quite sensitive to excessive heat. Herbivores, in particular, will struggle as their food sources dwindle. Smaller mammals fare somewhat better, needing less oxygen. Their surface-to-volume ratio aids in breathing, and they can dissipate heat more efficiently than marsupials and monotrem's. Birds in colder climates might also have an edge, being smaller and requiring less oxygen. Migratory birds, with their ability to travel vast distances, would be better equipped to find cooler refuges. But even those havens will shrink as temperatures rise, likely found only at higher altitudes, limiting population sizes. Ectothermic vertebrates, fish, amphibians, reptiles, may surprisingly be better adapted than us warm-blooded creatures. They could potentially live longer due to their resistance to high temperatures and lower oxygen needs. Of course, young amphibians might struggle to find enough water, and while freshwater fish will suffer as water evaporates, marine species have the relative advantage of the vast ocean. Ambient temperature, you see, drives metabolic rate. Higher temperatures mean faster metabolism, increased food consumption, and potentially more problems for already stressed species. Even the sex determination of some reptiles, dependent on temperature, will be thrown into chaos. Perhaps invertebrates will indeed be the last to remain. Before animals as we know them even existed, some insects could endure incredible heat. Terrestrial life is initially more vulnerable than marine life, I believe. The loss of land vegetation could disrupt the flow of nutrients to the oceans, affecting marine ecosystems, even those near volcanic vents. An animal's lifespan will then hinge on the half-life of oxygen in the atmosphere, which could last for up to 100 million years after plant extinction. Certain cyanobacteria and phytoplankton could persist, tolerating extremely low levels of carbon dioxide. This would continue until the atmosphere becomes utterly inhospitable to any form of photosynthesis. Researchers studying fossil evidence from Colombia suggest that some animal species might cling to existence even after most life vanishes. Studies of the Cambrian explosion are helping us understand how future climate change might play out. Rising global temperatures due to solar warming will lead to lower oxygen levels and, ultimately, mass extinction. Initially, it was believed that insects, lizards, birds, small mammals, and marine life would survive. But without a constant source of oxygen from plants, most animals would likely suffocate. Even with stable photosynthesis, the relentless increase in global temperatures will slowly erode biodiversity. We are already seeing this process unfold. Animals will be driven to migrate to polar regions or even underground, surviving mainly during polar nights and hibernating during polar days. But eventually, most of the Earth's surface could become unbearably hot, transforming into arid deserts with life concentrated primarily in the oceans. Even then, the reduction in organic matter in the soil and the decline of dissolved oxygen in seawater will cause many marine species to disappear. This process, mirroring what happens on land, could begin with freshwater organisms and eventually affect invertebrates, especially those that don't depend on living plants, like termites or worms near hydrothermal vents. Without enough carbon dioxide, photosynthesis becomes impossible. Without plant life, there's no free oxygen or ozone layer. The result is intense ultraviolet radiation reaching the surface, potentially leading to the death of multicellular life forms. Something similar, I've read, may have happened roughly 800 million years ago, when eukaryotes disappeared, leaving only prokaryotes. The sun, you see, relies on nuclear fusion reactions in its core, converting about 500 tons of hydrogen every hour. This alchemy gradually decreases particle density, because forming a helium nucleus requires 4 hydrogen nuclei. The lower the particle density, the more the core compresses under gravity. The higher the temperature, the more efficient the process. The sun's brightness, I've learned, is not a constant. It increases over time, driven by the intensity of thermonuclear cycles deep within its core. This growing intensity has been happening for billions of years, and while our Earth has a built-in system to regulate carbon dioxide and maintain a stable climate, it simply cannot keep pace with the speed of change we're experiencing now. Even as hydrogen burning slows within the sun, its activity is actually increasing. Its temperature has been steadily rising since it began its journey some 4 billion years ago. I find it fascinating to think about how life on Earth has managed to persist for hundreds of millions of years, thanks to a delicate balance between solar radiation and the greenhouse effect. For a long time, the mass of the Earth remained virtually unchanged, with a near equal exchange of water entering and leaving the mantle. This balance is essential for maintaining liquid water on our planet, a critical condition for life as we know it. But now, the amount of greenhouse gases in our atmosphere has increased significantly, disrupting that delicate energy balance. This creates an additional layer, leading to global warming. The Earth's silicate carbonate cycle, a regulatory system for carbon dioxide, operates on a timescale of about 1 million years. Unfortunately, the global warming we face is happening far too quickly for this cycle to be an effective solution. Since the sun converts hydrogen into helium, its average molecular weight increases, leading to a rise in core temperature and speeding up the fusion reaction. This gradually increases the star's luminosity, and its impact leads to an increase in energy emissions. If ocean water evaporates rapidly, marine species might have a better chance of survival than freshwater species, simply because of the larger volume of ocean water. Ambient temperature affects metabolic rate, and an increase in ambient temperature may lead to an increase in metabolic rate, and therefore more food intake. Reptile species whose sex determination depends on temperature will be more sensitive to increasing temperatures. Invertebrates may become the last animals on Earth, as they can survive in extreme temperatures. Before all kinds of animals appeared, some insects, such as beetles, could withstand temperatures up to 56 Celsius. Terrestrial life is initially more vulnerable than marine life. The loss of land vegetation may lead to a reduction in the amount of nutrients reaching the oceans. In turn, this can affect marine ecosystems, such as animal populations near volcanic vents. The lifespan of animals will depend on the half-life of oxygen in the atmosphere, a period that may last up to 100 million years after the extinction of plants. However, some cyanobacteria and phytoplankton can survive without plants because they can tolerate very low levels of carbon dioxide, such as 1 part per million. This can continue until the atmosphere becomes too empty for any form of photosynthesis. Researchers have used fossil evidence from the Isla Bourgeois in Colombia to suggest that certain animal species may persist even after the extinction of most other forms of life on the planet. British Canada studied climate during the Cambrian explosion and used this knowledge to predict how the climate will change in the future. Global temperatures are expected to rise due to solar warming, leading to lower levels of oxygen in the atmosphere and ultimately mass extinction. It was originally thought that certain types of animals, such as insects, lizards, birds, and small mammals, as well as marine life, will be able to survive. But without the constant oxygen source provided by plant life, most animals would likely die from suffocation. Even if enough oxygen in the atmosphere, the continued rise in global temperatures will lead to a gradual loss of biodiversity. This process has already been observed in recent years. Animals will be forced to migrate to polar regions or even underground, where they can survive mainly during periods of polar night and hibernate during periods of polar day. Unfortunately, in the future, most of the Earth's surface may warm up significantly, leading to the formation of arid deserts, and life will be concentrated primarily in the oceans. However, due to the reduction of organic matter in the soil and the reduction of dissolved oxygen levels in seawater, many marine inhabitants may disappear. This process may begin with freshwater organisms and will eventually affect invertebrates, especially those that do not depend on living plants such as termites or worms that live near hydrothermal vents. Without sufficient carbon dioxide, photosynthesis is impossible, and without plant life. Imagine a world without free oxygen, without the protective embrace of the ozone layer. It's a world where intense ultraviolet radiation would relentlessly bombard the surface, a death sentence for multicellular life. It's almost unimaginable, but that's the direction our planet is slowly heading. About 800 million years ago, all eukaryotes vanished, leaving only the hardiest prokaryotes to carry on. To fuel the sun, nuclear fusion reactions occur in its core, converting approximately 500 tons of hydrogen into helium every hour. This process leads to a gradual decrease in the density of particles within the sun. As the density decreases, gravity compresses the core. The higher the temperature, the more efficient the thermonuclear cycles become, and the more energy is released, causing the sun's brightness to increase over time. This increasing brightness is accompanied by a greenhouse effect, which has been vital in maintaining a stable temperature on Earth, save for periods of glaciation. This stability has allowed life to flourish for hundreds of millions of years. For a long time, the amount of incoming and outgoing water from the mantle remained almost equal, crucial for keeping water in a liquid state. Maintaining a balance between absorbed and emitted solar radiation, ensuring an optimal temperature, is the most vital condition for the existence of life as we know it. However, the increase in greenhouse gases in our atmosphere has disrupted this delicate balance, leading to global warming and additional layer-trapping heat. The Earth possesses a regulatory system known as the silicate-carbonate cycle, which naturally regulates the amount of carbon dioxide in the atmosphere, helping to maintain a stable climate. But this process operates on a timescale of about 1,000,000 years, far too slow to counter the rapid global warming we face today. Even as the combustion of hydrogen slows, the sun's activity increases. Temperatures have been steadily rising for about 4 billion years since the sun began its journey. At the beginning, its luminosity was approximately 70% of its current level, and by the time of the Great Oxygenation Event around 2.4 billion years ago, it had reached 85%. For the next billion years, the sun will continue to produce nuclear energy by converting hydrogen into helium, a process common to almost all stars. As the sun converts hydrogen into helium, its average molecular weight increases, leading to a rise in core temperature and an acceleration of the fusion reaction known as the proton-proton chain. This gradually increases the star's luminosity, leading to an increase in energy emissions, making the star glow even brighter. Almost all the energy needed to operate the Earth's dynamo comes from its core. It's expected that within 3 billion years the inner core will absorb a large part, if not all, of the outer core, resulting in a nearly completely solid core made of iron and other heavy elements. The remaining liquid shell will consist of lighter elements less prone to mixing and dynamics. Plate tectonics occurs due to heat transfer from the Earth's core to its surface. Heat transfer through the mantle sometimes occurs through convection, which, combined with thermal conductivity, releases heat when it reaches the crust and is pushed out by new streams. This horizontal movement at the top of the mantle drives the movement of tectonic plates. However, as the Earth continues to rotate and cool, the liquid outer core gradually solidifies. This solidification reduces convection in the mantle, limiting the strength of the plates. In 3 billion years, the plates will eventually stop moving and convection will cease altogether, ending plate tectonics. If plate tectonics ends, the Earth's interior will cool less efficiently, slowing or even stopping the growth of the inner core, potentially leading to the loss of the dynamo. Without a dynamo, the Earth's magnetic field will weaken rapidly in about 10,000 years. The disappearance of the magnetosphere will lead to further erosion of light elements, especially hydrogen, from the Earth's atmosphere, making conditions less favorable for life. In about 4 billion years, the increase in temperature on the Earth's surface will cause a runaway greenhouse effect, creating even more extreme conditions, perhaps even more extreme than those on Venus today. This will lead to the heating of the atmosphere and an increase in surface temperatures above 500 hours. In some places, the planet's surface may melt, but most of the atmosphere will remain until the sun enters its giant phase. At that point, the Earth's biosignatures will disappear, replaced by features caused by non-biological processes, erasing all traces of the history of life on Earth. After 4.5 billion years, the interaction between the Andromeda Galaxy, M31, and the Milky Way will form a new galaxy called Milkomeda. The Andromeda Galaxy, a spiral galaxy, contains up to 1 trillion stars, compared to the 300 or 400 million in the Milky Way. It's formed by gas and dust and has a flattened shape. It's almost impossible to imagine, but our own Milky Way galaxy is hurtling toward a cosmic collision. Andromeda, a spiral galaxy containing a central bulge, was located 2.5 million light-years away. It has always been the closest galaxy to us, and it's currently approaching at a speed of 120 kilometers per hour. At first, it seemed this collision wouldn't happen. The galaxies were so far apart, but the stars began to intersect, separated, and now that unusual choreography will lead to a closer encounter. The gravitational forces acting during the interaction have significantly altered their orbits. In about 2 billion years, this collision will result in a giant system with very little gas. They believe this new galaxy will be named Interstellar or Milka. Unlike its predecessors, it will have an elliptical shape, its stars scattered throughout a sphere. The good news? This collision will likely not affect the orbits of the planets in our system. The distances between stars are so vast that the probability of them colliding is extremely small. Any disturbances will be caused by activity in the neighboring galaxy. While these events could impact our solar system, the Sun and planets should remain mostly unaffected. The new galaxy will experience active star formation, but as the remaining gas depletes, this will cease, and the new galaxy will slowly fade, just like its newborn stars. Then, in 5 billion years, the Sun will leave its main sequence and begin to transform into a red giant after exhausting its hydrogen reserves. It will sustain itself through the energy released by the fusion of hydrogen nuclei in its core. This energy powers a frantic flow of sharp particles that exert powerful press on the outer layers of the star, keeping it in a state of expansion rather than collapse. Until then, this balance will be maintained, but after 5 billion years, the situation will change. Although the Sun is still full of nuclei, there's almost no hydrogen left in its core. During the process of hydrogen fusion, helium is formed, and the nucleus is heavier and denser than hydrogen. Helium is found in the core of the Sun, where the temperature is above 15 million degrees. For thermonuclear fusion of hydrogen, you need a temperature of about 10 million degrees. But for helium fusion, you need about 100 million degrees. When the Sun approaches this threshold, helium begins to replace hydrogen in the core, which leads to a decrease in the fuel supply for thermonuclear fusion. As a result, the press required to produce energy is reduced, and gravity increases sharply, causing the Sun to explode when its gigantic mass collapses on itself. Despite the extreme press and temperature, the melting of helium is not yet possible, so hydrogen enters the second phase. Thermonuclear fusion occurs in a thin shell around the helium nucleus. As hydrogen burns at an incredible rate, the force of gravity becomes significantly stronger. The Sun expands to enormous sizes, reaching over 100 million kilometers in diameter, almost 100 times larger than its current diameter. It turns into a pulsating red giant, becoming thousands of times brighter than it is today. This process will be completed, and the Sun will become a red dwarf, leaving its main sequence. The planets of the solar system will be directly affected by these changes. The Sun, with its reduced mass, will exert a weaker pull on the planets, allowing them to move into lower orbits. Although the distances to the planet seem enormous, they are moving at enough speed to get ahead in the space race. Mercury, trying to resist the increase in the diameter of the Sun, fails and is absorbed by it. For a short time, it even evaporates, and its orbit becomes wider. Venus, however, fortunately escapes this fate, as the Sun stopped expanding just before it was supposed to enter a new orbit. At the same time, Earth also begins its movement. The ions on Mars revolve around the Sun in sync with the Earth. The average temperature on Mars will be several thousand degrees. Imagine what sunrise would look like from Earth. Instead of a pleasant, warm, and joyful yellow disk, we'd see a giant red circle, slowly sinking below the horizon. Soon, Mars will suffer the same fate. The fate of planet Earth is also beginning to change. The atmosphere be starting to warm up, and possible life forms may not survive this process. No more than 1 billion people might survive on this planet. In 1,000 years, 2 new orbits will take their place in the habitable zone of our planet. In the solar system beyond the orbits of Jupiter and Saturn, there are planets that, although not ideal for life, may be suitable for the emergence of primitive life forms. Jupiter, for example, has water in its clouds, and Saturn is made entirely of gas. Its satellites, like Enceladus and Titan, could be suitable sites for the origin of life when their temperatures rise. However, unlike these planets, the surface of Earth will likely not be hospitable to life. Most of Earth's atmosphere will gradually dissipate into space, and the planet's surface will turn into an ocean of lava with floating continents of metals and oxides, as well as icebergs made of refractory materials. The temperature will constantly increase, significantly exceeding 2,000 degrees. The fastest phase of the Sun's expansion as a red giant will occur in its final stages, which will last about 7.4 billion years. The Sun's story won't end as a red giant. I find myself captivated by the sheer scale of time involved, the almost unimaginable processes unfolding at the heart of our star. As hydrogen nuclei continue to merge around the core, more and more helium accumulates, and the temperature keeps climbing. This cycle sustains the fusion of hydrogen in the shell around the core, accelerating its rotation and increasing the flow of helium towards the center. This phase, a mere blink in cosmic terms, will last for about 500 million years, until the core finally reaches the temperature needed to fuse helium. This helium fusion, leading to the creation of carbon and oxygen, will be marked by a spectacular eruption, a transition of the Sun into a subgiant structure. But even this new equilibrium is fleeting. 100 million years after that transition, carbon and oxygen nuclei will, in turn, displace helium from the atmosphere, just as helium displaced hydrogen before. The core will expand, and the combustion of oxygen and carbon will require even higher temperatures, at least 600 million degrees Celsius. It's a staggering number, almost beyond comprehension. But this time, the core won't be able to reach that temperature. Its mass simply won't allow it to resume nuclear reactions. To reach the temperatures needed to fuse carbon and hydrogen nuclei into heavier elements, the Sun would have to go through several more stages. At the start of its life, it accumulates energy, gradually releasing it as light and heat. During this process, helium fusion occurs deep within the star, compressing the core. Yet when the temperature becomes high enough, the Pauli principle steps in, preventing further compression. This quantum mechanism, acting as a kind of repulsion, prevents electrons from being compressed further, leading to their separation. As a result, the Sun stops contracting, and the outer layers begin to expand and cool, preparing to disperse into space. Eventually, all that remains is a ball of carbon and oxygen of incredible density, a white dwarf. This white dwarf will continue to glow for billions of years, but the fusion reactions will have ceased. The temperature just won't be high enough anymore. The Sun's thermal energy will slowly dissipate into space, leaving behind only a dark, cold sphere. In about 9 billion years, the mass of the Sun will be only 54% of what it was originally. At the very end, our Sun will become a white dwarf, composed of carbon and oxygen. Its core will be dead, but it will still exert its gravitational pull on the planets, comets, and asteroids that orbit it. All the planetary orbits will expand. If the Earth still exists then, its orbit will be twice as far from the Sun as it is today. In this new orbit, the planet would be a dark, icy world, completely devoid of life, orbiting its star at a slower speed due to the increased distance and the Sun's weaker gravity. This will continue for more than 4 billion years. Then, the white dwarf Sun will cool to a temperature of about 2,000 degrees. Its luminosity will drop to less than 3/millionths of its current level, and its heat will no longer be measurable. It will become invisible to the human eye, its radiation too weak, drowned out by the cosmic microwave background. The Sun will fade away, leaving behind only memories of its former glory. Gradually transitioning from a white dwarf to a black one, our planet faces prospects of destruction that are not mere speculation, but based on the scientific predictions we've pieced together. While we have this knowledge of what awaits Earth in the distant future, our immediate future depends on the choices we make today. This long-term prospect raises important questions about the future of life on Earth and our responsibilities as a species. Recognizing this potential future requires us to deepen our scientific knowledge and develop strategies for preserving our environment. We must find innovative solutions to preserve biodiversity, the extinction of humanity. It might seem far off, something on the scale of natural evolution, not human time. But that's exactly why it demands our attention. To truly grasp these vast phenomena and their potential consequences, I believe we must relentlessly explore and understand the world around us. The more I learn, the more I feel the weight of our responsibility to protect the environment. It's imperative that we seek innovative paths toward a sustainable future, not just for ourselves, but for all the generations to come. In my view, this relentless pursuit of scientific progress is truly our only real hope of avoiding what feels like an increasingly imminent threat.